Hello, everyone. My name is Rajiv Dada. I'm the chief engineer at GE Research in upstate New York in Schenectady. As you know, that GE very recently split into three companies. GE Vernova is the name of the energy company of GE. At the research center, we are also now split up in three centers co-located in the same place. So thanks for inviting me to present today, and I'll just provide our thoughts on advancing the state of the art, particularly related to the power processing part. And I'll talk more about the integrated power electronics, which is really the topic that, it's core to what we do. So if you look at how grid-connected solar PV installations are done today, with state-of-the-art power electronics. Typically, the DC output of the panels are connected to what we call as DC optimizers, which are DC-DC converters. And you do the maximum power point tracking through those DC-DC converters, and they provide a fixed regulated DC bus. And the reason for that is that you get a better utilization of the downstream power electronics like the inverters. And it also provides a seamless way to actually connect your energy storage. Now, this DC voltage, depending on the system, would vary. It could go from a few hundred volt to, for most of the large utility connected systems today, it's about 1.5 kV. One thing you have to keep in mind that when we are connecting into the grid, right, at medium voltage, you need really a bulky transformer. Another aspect of today's design is that most of the way these panels are connected together are at relatively low voltage. So there is a lot of copper in existing installations, and so they're heavy and expensive. And so if you look at this system and try to kind of, just replicate for a space application or a remote application with very high power density, it may not directly, translate. So what would be an approach would be to integrate the power electronics or bring the power electronics as close as possible to the panels, and then raise the voltage as high as possible. Again, it would depend on the application. And this would really need very high density power electronics if you want to kind of integrate the power electronics to the panel. Now, what you could do then is that you are actually doing the maximum power point tracking at the panel level. So every panel essentially provides you a high DC voltage. Again, high is a relative term depending on the application that you're using it for. But the requirement would be then, this DC-DC conversion needs to use some kind of a galvanic isolation so that now you can have a very flexible system which you can, and modular, that you can connect together with and have a means of very rapid installation. So what's the challenge? The challenge is actually in all this power electronics is to bring essentially high power density, high efficiency, and high voltage simultaneously. And you can optimize for one or two, but optimizing three is actually very, very challenging. And that's where all these technologies that I kind of listed are very relevant. Specifically, when you are talking about DC-DC converters, right, very high gain converters going from a low voltage to very high voltage is challenging at high efficiency. So that's one. Then it has to be very low profile, so you have to use planar magnetics. And we are talking about high frequency magnetics going from, hundreds of kilohertz to maybe a megahertz. And obviously the target power densities that we have today are essentially have to be improved by a factor of 5x at least in order to reach the numbers that I saw today in the chart. Again, they have to be divided from and extracted from an overall system level. So these are highly challenging aspects. And I think with the work that we have done over the last, I would say 20 plus years in high frequency magnetics with wide bandgap devices, this could be very, very relevant, particularly integrating these electronics at a panel level.
Thank you.
Yeah.
Next speaker is from Microlink Devices.
All right, good afternoon. My name is Roger Welser. I'll be presenting for Microlink Devices, discussing our flexible, lightweight, high-performance photovoltaics. As a bit of a background, Microlink Devices is an ISO 9035 materials and device manufacturer that was established in the year 2000 and is located in Niles, Illinois. What Microlink brings to the table is a flexible, lightweight ELO solar cells and sheets that have an industry-leading high specific power of around 2 kilowatts per kilogram, which is enabled by an epitaxial liftoff or ELO technology, which I'll discuss in a moment. The cells and sheets are flexible and lightweight, high efficiency, and cost-effective. Microlink currently has a Hale IMM product that's available now, and we are working on a space-qualified version, starting that process now and hoping for the end of the year. Microlink cells are unique, and they can enable new system designs and approaches. They're thin, they're flexible, they can have novel integration methods, including conforming to curved surfaces, custom cell shapes, form factors, and microcells. There's also some interesting device physics and device architectures that can be opened up thanks to the ELO process, including infrared rejection and allowing the cells to operate at low temperatures in real-world operating conditions, and also pathways to further improve the efficiency, radiation tolerance, and resilience of the cells. There's also capabilities to be able to provide either all topside or all backside contacts. So the ELO process is a process technology based on a highly selective wet chemical etch that allows us to peel off the 3,5 epilayers from the original growth substrate. Showing here in the lower right-hand side is an example of a foil, 6-inch foil, and Microlink can do this over a full 6-inch substrate, peeling off all of all the epilayers, resulting in a flexible, thin, less than 30 micron foil. So the benefits, particularly for photovoltaics of an ELO approach, include low areal mass density. As the gallium arsenide substrate is removed, it's also potentially lower cost because the gallium arsenide substrate can be reused. It's high efficiency. We're currently using an inverted metamorphic structure in our Hale product, 3-junction, 3-5 structure, and flexibility. These cells can be bent without degrading performance. So currently, Microlink is producing flexible cells for the high altitude, long endurance UAV applications. These are lightweight, high efficiency, around 30% cells that can conform to the curved surfaces. Microlink is also in the process of qualifying solar sheet for space power, looking at a couple of different cell levels for a couple of different fluence levels. We're providing both cells and a sheet, integrated sheet, and an example which is shown here in this image, and it's flexibility, being able to bend around a curved surface. And we hope to have that product qualified towards the end of the year. There are a number of other device physics options that become available when you have an ELO structure. Let's begin to try to highlight some of that in this chart here. For example, because for an ELO solar cell, you can peel the substrate off, peel the epilayers off the substrate and have a back reflector then right next to the device. You can build in a high quality broadband mirror that can reject infrared photons. And in this example here, this is a slide taken from a presentation from Martin Kroon at Airbus a couple years ago, comparing a couple of different device architectures. But what he points out is that with an ELO solar cell, with this infrared rejection built into it, it can operate at a lower temperature. And that's kind of what's illustrated with the 3 red circles here, is that compared to a traditional structure on a germanium structure, a 3-junction ELO solar cell can operate at a cooler temperature. A dual junction can even operate at a much lower temperature. And this kind of the being able to peel off the epi layers allows a bunch of different other kind of options in terms of optimizing the device that we can work on improving both beginning of life, end of life, and resilience of these type of device structures. So we think this is something that might be of interest to this community here and this project and program in particular. So in summary, Microlink has demonstrated flexible high efficiency photovoltaics kind of a unique approach, a unique architecture, and we would love to talk to people and see if it would work for your applications. Thank you.
Thank you. Next up is Apogee Semiconductor.
5 minutes. I guess this is what Tinder feels like. Okay, so Apogee Semiconductor, we're a US-based fabless semiconductor company. We design, manufacture, test, and sell semiconductors for primarily the commercial space market, although we've also done work for other organizations and more extreme environments. We're basically focused on getting the cost down where new space. Our goal is to reduce the cost of silicon to closer to commercial prices, get the performance up closer to commercial prices from an electrical performance perspective, but get the radiation performance similar to traditional radiation hardened electronics, which tend to have 1980s level electrical performance metrics and 1980s big space costs. So as I say, primarily we're targeting towards small satellites and large constellations, but we also do GEO products as well. We work with commercial foundries. Part of our technology is that we can take commercial bulk silicon processes and make rad-hard ICs, partly by rad-hard by design, a little bit of architecture is involved in there. And sometimes there are some small tweaks to, well, it's definitely tweaks to the layout of components and sometimes some minor tweaks to the process. So why are we interested in this opportunity? We have a very successful track record. We have had won 2 NSF grants for different, entirely different programs. We've had multiple programs with Space Force, Air Force, NASA, 2 programs with NASA. We have a history of 100% every single time delivering what we said we would deliver. We have patented technology that we believe would benefit the mission. We have experience, as I say, in high performance commercial. Our team of engineers have deep experience in both rad-hard, but also the bleeding edge of commercial. And we can get into this in more detail, but we know an awful lot about fully integrated switching converters with onboard FETs. We know an awful lot about making power transistors rad-hard and what the mechanisms are. We know an awful lot about power switches, all of which are very interesting things for solar. So as I say, we can do 300K rad TID, 75 MeV SEE, and bulk CMOS. We have an established tool chain. This is part of what makes us successful. A lot of the traditional space components are built using 1980s technology because the tool chain does not support using many transistors to solve your problems. We spent the first 4 years developing a tool chain that allows us to use 250,000 transistors where your predecessors would have used 200. This may sound like wastefulness, but it's not. In commercial, we routinely throw a lot of transistors at a problem to improve performance, and we can do that. So some examples of results of our technology, you can go and look at our commercially available products. But this, let's see, does this work? Well, if you could see it, the green thing over there is a block diagram. The blue thing is basically a die image. This is real silicon. This was a program that we developed under NASA funding at the request of JPL. This is a multi-topology power controller that's rad-hard and has extensive, and you can probably make out from there, there's 3 of everything. So this is fully triply redundant, pin-to-pin, on-board DSP with special additions in there to make it rad-hard. So we've talked about why our technology is important, why we're different. We know an awful lot about making rad-hard, high-performance silicon, and we're looking to partner with somebody who has experience in multi-junction cell design and solar panel design, because that is not our area of expertise, but I think we have some really interesting ideas. And if we can find the right partner, I sincerely hope that you swipe right. Thank you.
Thank you. State University of New York, Buffalo.
Yes, sir. Thank you. Thanks for the opportunity of presenting our research about perovskite solar cell and the strategy of stabilizing the interface. My name is Wan Yini. I'm an associate professor at the Department of Physics at the SUNY Buffalo. And I'm going to introduce perovskite for high efficiency photovoltaics for this lightning talk. And as we know, perovskite are novel emerging solution-grown semiconductor to build ultra-thin solar cell with a high efficiency that is on par to the silicon single junction cell. And perovskite is follow a general formula of ABX3, which is a 3D perovskite typically used for high efficiency solar cell. And the material have a tunable composition. That means we can widen the band gap to build a suitable top junction solar cell for tandem that can potentially boost efficient silicon bottom cells efficiency over 40%. And also, pioneer work have shown that, including one of my colleagues at the SUNY Buffalo, Professor Ian Sellers, have shown that perovskite have a very good radiation tolerance compared to silicon. That makes it very suitable for space application. However, tuning the band gap of 3D perovskite, we have to alloy the halide in the structure, which make the material thermodynamically unstable. So I want to introduce 2D perovskite is an intrinsically stable wide bandgap top cell for tandem. And the 2D perovskite, very briefly, has an architecture still with a 3D building block, but separated with the organics, forming a layered structure. So this organics, on one hand, build this 2D quantum confined structure that widen the bandgap to be 1.75 eV. On the other hand, can stabilize the structure to make them intrinsically stable. So we have an initial optical simulation that shown this 2D perovskite have a really good band gap matching with a low gap semiconductor, for example, silicon, but it could be other low gap semiconductor, and we can potentially make our high efficiency, high power density tandem cell with a perovskite, 2D perovskite. And our early work have shown that 2D perovskites are way more stable than the 3D. For example, we demonstrated pure 2D single junction cell reach 12% efficiency, but 3 times more stable than the 3D cell, and under constant illumination condition and under harsh high humidity condition. So it is an intrinsically more stable semiconductor. And also very recently, we have shown that 2D perovskite are solution-grown semiconductor. We can print them over larger scale. And here is a new study that we show by simple spin coating method, we can build 5 by 5 centimeter cell with a very reproducible efficiency all over the area with a higher efficiency over 15% now. So that means 2D perovskite are scalable that can be monolithically integrated over other low bandgap solar cell. And another perspective we are working on is trying to stabilize the interface. And this is one proposed N-type interface material, gallium nitride, that we developed recently to interface with the 2D perovskite. And we built a PAN diode putting 2D perovskite over gallium nitride. And the gallium nitride is an N-type high mobility semiconductor. It is also a red hard semiconductor with a self-healable property after radiation bombardment. So we think this interface will be suitable for space photovoltaics. And this is one study that we interface 2D perovskite with a gallium nitride nanowire, and we got a very robust interface. And the interesting, our students have exposed this hydrojunction under 200 cycles of X-ray irradiation in ambient air, and there's no photocurrent degradation from our junction. So that means it's a chemically robust interface and also radiation hard hydrojunction that could be potentially useful for space photovoltaics. So we are interested in developing 2D perovskite as a wide bandgap top cell for thin film tandem cell for space with a radiation hardness and potentially made in a paper thin kind of a flexible geometry to deliver high density and lightweight photovoltaic. So that concludes my talk. Thank you so much.
Thank you. Next up is Celestial Incorporated.
Hi, I'm Vince Hearn. I'm the head of government business development for Celestial. We're here to exist to deliver abundant energy in space. We've developed silicone solar technology with breakthrough radiation hardening in a rollable package that is currently in space today. We have unlimited scaling at 1/10 the cost of 3.5 cells. We meet Solstice goals by substantially reducing the degradation of silicone solar modules in space to maximize their lifespan and energy yield. We create the first silicone cell that can cure radiation damage at normal operating conditions, which solves its radiation-induced degradation. Second, we developed robust cell-to-cell interconnects that don't fail and achieve minimal degradation, even in the most stressful conditions in LEO. Finally, we reduced yellowing of the transparent cover layer by using a protective capping layer. This graph shows the degradation of the power modules over time. As you can see, all of these innovations allow movement of the silicone solar modules from the orange curve to the pink curve. In addition to reducing the degradation rate of silicone modules in space, our technology is perfectly suited to be integrated into a silicone perovskite tandem to match the efficiency of the incumbent 3.5 cell. If perovskite layers can be made radiation hard, the bottom Celestial cell and a tandem will self-cure radiation damage to produce an ultimate radiation hardened solar cell. And all of that is achieved at 1/10 the cost and with no scaling bottlenecks. We're based in Tempe, Arizona. We're made up of an expert team of space experts with vast experience and backgrounds. And as I said earlier, our products are in space and performing now. We also have 6 additional flights scheduled for 2024 and a 50K array for 2025. And in regards to scaling, we recently moved into a 27,000 square foot facility, providing up to 2,000 kilowatts a year. By 2027, we plan to have a 100,000 square feet facility and the ability to produce over 10,000 kilowatts per year. Our logical evolution for us is the ability to provide silicone solar cells for the operation of large scale systems. As human activity in space grows, so does the need for the large scale systems. A sustainable economy in space will require utilities, scale power generation, just like we have here on Earth. Celestial is well positioned for the future of space. We look forward to teaming, and thank you for your time.
Thank you. University of Maryland.
I would like to give our contribution to the photovoltaic part of the Solstice program, specifically the organic photovoltaic part. My name is Lou Martinez Miranda, and I will be telling you of some of the contributions that my colleagues have made. So we have been investigating how to improve the efficiency of the OPVs by the addition of a small molecular dopant, in our case, a liquid crystal. The liquid crystals have the ability to self-align, and we will exploit them. As a dopant, they are hole carriers. Dr. Salamanca Riva and I have investigated possible hybrid photovoltaics with a mixture of CNO nanoparticles and a liquid crystal, and characterize them structurally via JICS and TM, as well as electrically. More recently, Dr. Borunda and I have been studying how to convert the liquid crystals into nanowires by physical means through the roughness of the interface between the 2 principal constituents that participate in the charge separation in the photovoltaic. You can see that pictured in figure 1. Using that knowledge, and figure 2 presents one of the possible nanowires that we will obtain. So using the knowledge of how the surfaces can be prepared, which I provide, Dr. Borunda investigates theoretically how the arrangements are such that his theory can choose the 2 preferred arrangements, i.e. the arrangements that have the least amount of energy. This allows us to observe how the surfaces can, to observe if the transfer inside the nanowire can arise from the overlap of the p orbitals in the liquid crystal, which can add to the efficiency obtained through the percolating structure due to the polymers in the OPV structure. Dr. Salamanca Riva and I will use the techniques mentioned in the last slide, and Dr. Burunda will contribute current voltage measurements in addition to his work on theory. The results of this research will serve as the surface of the Earth, results that can be used and or compared to Dr. Al-Sheikhli's research. Dr. Al-Sheikhli studies what happens to polymer materials in the Van Allen belt or situations that are similar to Van Allen belt that are obtained here on Earth. The Van Allen belt is a zone of charged particles that are captured by the Earth's magnetic field. There are 2 Allen belts, as can be seen in figure 3. And the selected polymers will be irradiated with gamma rays, electron beams, alpha particles, protons, and neutrons. And they will be analyzed with EPR, Raman, NMR, and FTIR, amongst others. In his studies, Dr. Al-Sheikhli will use polymeric materials which contain phenyl groups to enhance the resistance to ionizing radiation. Also, he will avoid any polymeric materials which contain glycosidic bonds and fluorine atoms on the backbone of their chains because they undergo fission reactions upon radiation. So these can help us to choose the appropriate materials for the Earth experiments. If we succeed, we will have a method for combining the surface studies and those in space, and we'll have a good data that can be combined with theory. The midterm results will consist of looking at the results of irradiation and comparing it to the results on the Earth's surface. The final result will consist of looking at the second one and observing if we can get consistent results. Thank you.
Rochester Institute of Technology.
Thank you. So I'm Seth Hubbard from RIT, and I'm representing 3 potential team members, myself, Chris Gibank at the University of Michigan, and Brent Fisher, who's affiliated with Acelaprint. Our approach and what we have some expertise in is concentrating photovoltaics for space. Some of the advantages of that are the higher efficiency that you can get, perhaps the shielding, and then the increase in capacity you can get going to smaller cell sizes. The approach here, though, is to get away from things that have moving parts or other optics and look at micro-concentrating designs, which Chris has quite a bit of expertise in the optical design. RIT has background in growth and fabrication of these devices, and Acelaprint uses microtransfer printing, which I'll talk about that in a second. So the micro-concentrating photovoltaic approach you can see here uses a small lenslet array and a small micro-concentrating cell that is bonded on the back of the lenslet array with the back of the cell facing the sun. So you're getting the illumination from the bottom, which helps with the radiation tolerance. And then everything's put together in a package like this. This is some initial results from Chris's group. You can see the cells here in black and the lenslet array around it and on top of it. These I'll show you on the next slide what the efficiency, but the approach here uses relatively low concentration so you can keep the acceptance angle relatively large. Some of the initial work from Chris's group, which you can read more about in his Joule paper, showed a small lenslet array with 26% efficiency and over 100 watts per kilogram specific power. Some of the approaches to go to higher efficiency again would be reducing the cell size, using multi-junction photovoltaics as the concentrator PV here, and then or even using some innovative 3 to 5 junction cells to push this up to higher efficiency. Our capabilities at RIT include MOCVD, so we can do arsenide, phosphide, and timonide based MOCVD. We've done quite a bit of work in photovoltaics, as you can see some from the IV curves here. We also have capability for fabrication. We have a 3.5 processing line in our clean room, at least at small scale. And my lab at RIT is pretty well developed as far as AM0 characterization, radiation characterization, materials characterization. I'll go through the whole list of stuff we have. But we also, as a group, have quite a bit of expertise in transfer printing. Transfer printing, if you don't know about it, uses a PDMS stamp and a release layer to pull these off and basically pick in place, but at a relatively small size. This has been done and demonstrated. Naval Research Labs and some of the people in this room and Semprius have done this for a number of years and achieved close to world record efficiencies by combining multi-junction cells with one another by transfer printing. We can do this at RIT, at least in prototype, and then also work with Acceloprint to expand this. We just bought one of these new, we just bought a new transfer print tool a couple of years ago and are in the process of qualifying it now, mostly with laser technology or lithium niobate. But easily do this with 3.5s. So good on slide. Yeah. In summary, we have some expertise in micro CPV for space. We have a team that has optics growth and transfer printing capability, and love to work with people.
Thank you. And SRI International.
Hey, hello, my name's Patrick Maeda. I'm a principal engineer at SRI, and I'm here today with colleague Dr. Anna Braun, and we're representing over 1,000 researchers at SRI, and the company does about several $100 million in government business, and a smaller amount, but significant amount in commercialization as well. We also will take what we developed under government funding and transfer it to an industrial base for production and manufacturing and delivery to commercial and government customers. So I prepared a bunch of slides here, which I won't be able to go into detail given the time, but I thought I'd provide them so people can look at them post the meeting and learn more about our institute. We are a nonprofit or research institute headquartered in Menlo Park, California, and but we have divisions across the country. We do have a strategic research area in space, and in addition to some of the SOLSTICE work that we're considering, we do quantum networking, LiDAR for long-range applications in space, and space telecom, laser comm, among others. So in terms of relevant experience to SOLSTICE, Park, formerly Xerox Park, is now under the ownership of SRI, and that occurred sometime last year. So we're still in the process of that transition. But while at Park, we did a lot of high concentration PV work and low concentration PV work. We incubated these two companies at Park and went all the way up to pilot manufacturing in both cases. We also have done some work in high efficiency luminescent solar concentration. One actually involves the use of split spectrum architectures to boost the efficiency. We also have done a lot of work in microassembly. We did some work in A2P and DARPA and ARPA-E Mosaic, which Mike Haney over there was the program manager for. We've done some stress metal work, and we have fabrication facilities for thin film and large area electronics. We also have done a lot of work in robotics technologies that can also be applied, including in this is also a lot of ML, AI, and CV, computer vision work. So I'm flying through the slides here, but I really wanted to get to this last slide because it kind of will indicate where we need help, right, as a prime. And it'll also give you an idea of where we can help, as a subcontractor. So, you can think about some of these areas. We'll also mention that we do a lot of work in advanced materials, metamaterials, metasurfaces, and so forth. Our group in Princeton, New Jersey, developed the high resolution CMOS imager has flown on 2 missions and is scheduled for 2 more missions, primarily with the Parker Solar Probe and Europa Clipper. And SRI is also involved in developing a space object and debris detection and monitoring system. I believe it currently with one of the agencies. In addition to some of our in-house capabilities, there are many other technical disciplines. As I mentioned before, we do a lot of work in AI, machine learning, and computer vision as well. So we can also apply some of that to this program. But I also want to take the time to maybe offer a couple of comments for the program. One is that it would be great if you could provide a quantitative example for EHY, energy harvesting yield, because it's a significant component of all the metrics. And because we like the fact that you've taken time to develop your BAA, because quite frankly, the concepts we developed based on the RFI are very different from what we did after you released the draft BAA. So if you could do more of that, that would be helpful. We also have a need for a high band gap solar cell. So,
We're going to take a 5-minute break while we switch over to the remote presenters. And by the way, the government is not here, does not watch the lightning talks. So I'm a contractor support, but so remarks like that, if you have a significant question for the program, send it as a question to the proposed alias, and it might be shaped into the BAA. So we'll do 2:10 will be the first remote lightning talk. Okay, thank you. We now have a sequence of remote lightning talks. The first one from Northwestern University. So go ahead.
All right. Hello, everyone. My name is Bing Chen, and I'm a research assistant professor in the chemistry department at Northwestern. I'm working with Professor Ted Sargent. So our optoelectronic research group is focusing on developing new materials for energy harvesting devices. So I'm very excited today to share our vision for the next generation solar cells using perovskite technologies. So when it comes to solar technologies, there are a lot of options available. On the high-end side, we have a 3.5 gallium arsenide-based solar cell. They offer the highest power conversion efficiency. However, they're very expensive, so you don't see them in everyday scenario. So they are typically used in price-insensitive applications like what we are talking about today in space explorations and military. So if you purchase a solar panel for a rooftop, you will likely choose a silicon panel with around 22% efficiency. So as a solar material scientist, we wonder if there are better materials available that combine the high quality of 3.5 semiconductors with the same or even lower cost than silicon. So I hope that I can convince you that such a material exists and it is perovskite. And the key is to realize multi-junction perovskite solar cells. So one advantage of perovskite is that it has really low fabrication costs. These materials can be produced using solution processing, making them is as simple as printing a newspaper using a perovskite ink. The other unique property to the success of perovskite solar cell is its band gap tunability. So we can tune the band gap from 1.1 eV to 3 eV easily, as shown on the right-hand side. So we can just tune them by changing the composition of the ink. So over the past decades, there has been a rapid development in the efficiency of perovskite solar cells. It has almost reached the level of a conventional technology like the silicon. We have just around 1% lower than the highest efficiency. I think the silicon is now at 27. This is not updated. Sorry about that. So the message is that it's amazing how perovskite technology can achieve from around 10% efficiency to more than 26% efficiency in 1 decade, which took silicon 40 years to achieve. So I want to highlight that our group at Northwestern is the current record holder of single junction perovskite solar cell. So as a perovskite has a very high optical absorption coefficient, we need only a few nano-100-meter thick thin film to absorb all sunlight above the band gap. Combining this high efficiency perovskite solar cell with ultra thin flexible PET substrate, it has been demonstrated to have the highest power to weight ratio. But we are not content about the single junction because there is a fundamental limit. The theoretical limit dictates that you cannot get higher than 33%. So that's why we're making multi-junctions to increase the efficiency limit. So last year, we made a major breakthrough in the all perovskite tandem field. We solved the problem that prevents photoexacted electrons to be extracted out from perovskite tandem. And we made a tandem cell that was most efficient, certified by NREL. So we are pushing the technology further by building triple junction solar cells. Earlier this year, we achieved a major breakthrough. Our team demonstrated the world's first perovskite triple junction solar cell, certified again by NREL. So you may argue that the triple junction efficiency is lower than a single junction. However, considering the relatively short history of research on this topic, specific perovskite triple junctions, we expect significant advancement in the next few years. We believe that the efficiency of the triple junction solar cell will surpass 35 with specific power more than 58 watt per gram. Thank you.
Thank you. Next up is Berkeley.
Hi, everyone. I'm Robert Palava-Podgorski. I'm a professor here at UC Berkeley. Sorry, I can't be there in person. I had to give finals this week. So I directed the Berkeley Power Energy Center. We focus on extreme density power electronics. Just want to acknowledge the men and women. In fact, a lot of women working in my group on this topic. And our research spans a wide range of applications and voltages and power levels. So all the way down from on the left-hand side here, DC-DC chip scale, sort of cell embedded power converters, up to the DC-AC sort of kilowatt scale inverters, up to hundreds of kilowatts and down to a milliwatt range. Really, our group specializes in really high density, really very high efficiency power converters. And there's two things that we focused on over the last several years is we're trying to exploit the higher power density of capacitors compared to inductors. You can see on the plot on the left-hand side here that capacitors store about 1,000 times more energy than inductors. We're building circuits that exploit that feature. The second feature we're trying to exploit is that power semiconductors have a scaling that favors low voltage devices. So a commonly used figure of merit here on the y-axis is QGRD is on. And you can see that you're actually better off. The figure of merit gets much, much better at very low voltage devices. So we're trying to build circuits that exploit capacitors and use more low voltage power semiconductors rather than single high voltage switches. So to give you one example of an application space where we done a lot of work, it's a 48 volt applications in data centers primarily at the moment, but also in automotive. And it's a nice comparison because everyone has to do the same voltage conversion. And what I'm showcasing here is a number of our hardware prototypes from 48 volt starting to say 12 volts, which might be applicable for a satellite system as well. And for that relatively small conversion range, we're achieving sort of on the order of 99% efficiency and a whopping 6,000 watts per cubic inch power density. And of course, if you think about machine learning and AI processors, they tend to need down to about 1 volt. So you have to do a lot more work with the power converter. And that range, you see that we get lower power density and lower efficiency, but still, as I'll show you, is the state of the art and the best performance in the world. So just to give you a highlight of what some of these converters look like. So we build these converters on the left-hand side where you see the schematic. We're using primarily capacitors and low voltage switches. And then we have to do less work with the magnetics. And this is a data center 48 to 12 volt, what we call cascade resonance switch capacitor converter. And we can get 6,000 watts per cubic inch in steady state, or 366 kilowatts per liter. And at peak, we can actually process close to 10,000 watts in a cubic inch. And again, achieving efficiencies even higher than 99% at times. This is an example that I think would be very relevant for this audience. We just recently this year published a 48 to 1 volt rad hard GaN solution. This was motivated by space applications. We use gallium nitride transistors. And what you can see is that we're pushing 50 watts of output. We're going from 48 down to feeding now a flying machine learning AI processor that needs to be lightweight. And we're actually able to get this 50 watt converter. It's about 2.6 millimeters thick, and it weighs 1.6 grams. So we're achieving this at a 31.6 kilowatts. That's kilowatts per kilogram, and 2,000 watts per cubic inch that we just demonstrated. To give you a sense for how this compares, we always try to compare to state of the art. And what we're plotting here is power density on the y-axis, system efficiency on the x-axis, and you want to be in the upper right-hand corner. And each converter that we're comparing here has actually 2 dots. The first dot, the upper dot, is the peak power rating, and the second dot is the peak efficiency rating. What you can see here is that the top 3 ones presently are all coming out of our laboratory. So I'm very pleased to say that we do have the highest performance of anything published to date. I want to end with where would these things work. So this was still pushing power density and efficiency. We have experience applying these in solar PV systems. In fact, we pioneered some of these what's called the sub-module DC optimizers that now are coming on market. But a decade ago or so, I did a lot of work in that space. We have experience working on space-rated power electronics. We work with industry and work with NASA JPL on rad hard applications. We actually have done flight qualified prototypes. So we have done the shock and vibration test for these type of converters on an airplane on the right-hand side, you can see here. And we also have a lot of efforts in extreme environments. We developed these for cryo-cooled power converters. So we'd be eager to partner with anyone that needs really lightweight, really efficient power converters and combining them with photovoltaics or whatever energy source that you have in mind. Thanks so much.
Thank you. Next up, Vicor.
Hi, can everybody hear me?
Yes.
Okay, so my name is Matt Renola. I'm from Vicor, and I'm here to talk to you today about our high-density rad-tolerant modules. If you would look at the picture of the hand with the four parts in it, think of that as one DC to DC converter. And this example shows a chipset from 100-volt solar array down to 0.8 volts at 150 amps. So the current solution is basically a isolated stage providing the 100-volt input. It's a K of 1/3 divided by 3, so you get a 33-volt output. And this will take a regulation stage down to a transformation stage to deliver the 0.8s at 150 amps. And we also have another rail here that's of the same architecture that's basically taking 28 down to 3.3. So this is a flexible solution for powering ASICs or FPGAs in space. It's rad tolerant, and it provides a 300 watt total power capability, power envelope. The PRMs can be placed at the at a distance from the VTM, so it's flexible, and it's a very small, compact solution for powering ASICs in space. And we have heritage as of last year with our lead customer. So inherent design flexibility, we can develop different BCM and VTM K factors so that it's not limited to just a 100-volt input. It could be a 48-volt input, a 28-volt input, or some other input. And we can develop different scalable parts to provide power distribution networks at very high power levels, very high current at the point of load. So again, this just shows, that this architecture is scalable. The first products that we've released are of the 100 volt part, but we are in development now with the 28, which is a K of 1. So it's 1/1, 28 volts in, 28 volts out, matches up with a 28 volt PRM and delivers the same 0.8 volts at 150 amps and 3.3 volts at 50 amps. So it's, again, very small, very compact for machine learning and AI in space. As the current at the point of loads start to increase, this is a very, very compact solution. Again, you can mix and match these. They can be paralleled based on voltages that you need. So it's a highly flexible architecture. It doesn't need to be just based upon the rails that we've identified, but we can quickly develop and adapt different rail voltages based on the technology. What we've done from a radiation tolerance standpoint is we use commercial products and we screen for both TID. So all the products undergo TID testing to certain levels. These products right now function at 50K rad and 35 MeV. So again, for LEO applications and some MEO applications with proper screening and, depending upon the duration of the mission, these can be relatively good solutions compared to what's out there in the market. Again, I talked about single event survivability. So we've picked commercial MOSFETs and we've done single event testing, and we've mitigated basically any of the latch up, any latch up from a controller standpoint that we see. We mitigate and have protected around that so that there's survivability, again, up to certain levels of in space. We talked about some of the mitigation. These include dual powertrains, so it's a redundant N+1 powertrain, so that if one of the powertrains gets hit with a single event, the other powertrain inside the module will pick up 100% of the load, and things will ride through and reset once everything gets back to normal. So that's built in and inherent into the part. Again, some of these parts are radiation, the single event immunity. There's robust component selections. We've derated the MOSFET. We've done latch up protection and reset internal. And this modular approach allows for a very quick development process internal to Vicor. Again, these are BGA components, so their standard dual side PCB has a dual side cooling.
Thank you.
Okay.
Next up is Arizona State University.
Hey everyone, I'm Nick Rolston at Arizona State University. Here to talk about some of the work that we've been doing in terms of metal halide perovskite photovoltaics, and how I don't need to repeat what's been mentioned, but that these can achieve very high specific power densities and are ideal for tandem configurations on whether it be other lower bandgap perovskites or on silicon. They have been demonstrated to have actually self-healability and also quite good robustness under radiation. Varying types of radiation here. This is showing proton radiation. And overall, though, there's a need to improve reliability and understand, truly like what are the right tests to validate lifetime. So our group does a lot of we produce perovskites at scale, but we also, our key areas of expertise are on thermomechanical reliability, on understanding the fact that these materials are extremely susceptible to delamination, and this happens under combinations of for varying reasons. One is that there's very poor bonding within the layers of perovskites, and additionally, there's a very large thermal expansion mismatch in CTE between the perovskite and the glass or silicon substrates that are typically used, and so this can lead to catastrophic challenges and failures under operational conditions. So our group is kind of really focusing on understanding how can we mitigate these types of failures, how can we design accelerated testing protocols and validate reliability for something like a 10-year mission in a much shorter time. So anytime you have a excuse me, any sort of tensile film stress that occurs, which can happen from, again, due to the large mismatch in thermal expansion coefficient, then you're going to have the accelerated degradation processes. So you have driving forces for ion migration, for chemical instabilities, and ultimately for mechanical failure as well. This can actually be quantified in terms of a mechanical driving force, and it scales with the square of the tensile film stress. So when these perovskites are cooled to very low temperatures, in whether it be in LEO or in general in the space environment, this is going to drive significant amounts of driving forces. And then when that value exceeds the material's fracture energy, the actual resilience of those bonds in the material, then you have catastrophic failure. So our group has developed approaches for measuring both fracture energy, tensile film stresses, doing in situ measurements, and understanding how we can mitigate these sorts of challenges. And so I'll just give a very brief example for conventional processing that is done with these perovskites leads to very large tensile stresses initially, and then over time, those stresses, they do reduce this is under thermal cycling between -40 and 85 Celsius. But as they reduce, you'll see after 200 cycles, those pictures on the bottom, they turn completely yellow. And so you see that there's, complete degradation. So we've used approaches to engineer in compressive stress from processing, and that allows for these materials to withstand, hundreds of these cycles. Now, of course, these need to withstand thousands of cycles in LEO, but these are just the bare films without any sort of cover or barrier layer. So it's just and is kind of the most aggressive form of just testing the film itself. So overall, our group is trying to work at the intersection between chemical, environmental, and mechanical stresses. And I just mentioned the fact that we're able to quantify these degradation effects and these thermomechanical properties in situ, along with also ionic measurements as well to quantify changes in structure in these perovskites, whether they be for single junction or multi-junction applications, particularly focused in this call for multi-junctions. And we're very open to working with folks that have more on the that are looking for someone who can provide perovskite processing experience and also thermomechanical and accelerated reliability validation. So my email is on the bottom, and appreciate your time. Thanks so much.
Thank you. Next up is UCLA.
Thank you very much. I will go on slideshow mode here. So my name is Ashwat Raman. I'm with the Department of Material Science and Engineering at UCLA. And today I'd like to share some of our capabilities and background on thinking about optical approaches to thermal management that may be relevant for high power and durability PV applications. So at its core, we think a lot about how at a material level we can control thermal radiation, both its transmission, absorption, spectral characteristics, directional characteristics, which can be quite relevant for a range of applications, as well as the fact that it is often static and fixed by the temperature of the radiating object. So what I'd like to do in this brief presentation is just highlight some previous results we've been done over the past decade, looking at material level strategies to control both simultaneously solar transmission or absorption, as well as infrared properties in ways that may be very relevant to maintaining, for instance, a higher power density PV architecture, whether in space on our Earth, at a lower temperature point. So as we all know, and this is going to be a central challenge for this program, PV gets hot under the sun. This is particularly challenging when we think about concentrator architectures and certainly in space as well. And there's both an aging issue as well as a relative efficiency degradation, which are going to be central to this, meeting the solstice targets. An effort I was involved in about a decade ago directly tackled this problem by asking a very basic question, which is, can we improve the emissivity of front surface glass, which is, of course, the front surface that we find both in space and in terrestrial applications for any PV module? And so The fundamental challenge we have is that glass is primarily made of silicon dioxide, and it has this giant dip in its emissivity that ranges between 8 and 10 microns. So the overall emissivity of front surface glass is around 0.84, 0.85. There have been strategies over the years that have tried to bump it up a little, up to 0.9. But we really asked, can we do better? And can we also preserve the same amount of sunlight going in to an underlying solar cell? Because we can't lose solar transmission into the actual PV cell. And so this was one effort where we introduced through a lithographic process, a wafer scale lithographic process, a photonic crystal, so periodic holes that were etched into the front surface of the glass. It looks something like this. So this is the top view, side view, and the spectral properties were very attractive because you could basically get the same amount of sunlight into the underlying solar cell, and you can overcome that big dip in the emissivity that was present with silicon dioxide, kind of filling in that hole and getting an overall emissivity that in excess of 0.9 and up to 0.95, which is quite desirable for both terrestrial and space-based applications. And we demonstrated this in terrestrial testing outdoors back in 2015. More recently, my group has also been thinking about directionality, which may be particularly relevant when we think about LEO applications, and asking whether we can enable thermal emitters that are broad spectrum, high radiance emitters, but that are highly directionally selective. So you have high emissivity through a particular angular range, but over a broad spectral range through that same set of angles. And so this is a fundamental capability we demonstrated in a paper in Science in 2021 using a range of strategies. Here it's demonstrated using very commonplace semiconductor oxides and some optical properties they have. And you can actually visually see this with thermal images where you can have something that's very reflective and low emissivity at certain angles, and at high angles, it's actually very highly emissive. So this may be a useful capability. And more recently, we've demonstrated that you can actually achieve this with doped semiconductors, some of which might be part of a 3.5 PV architecture. Finally, in the last minute, I want to highlight an effort I've been involved with, which is on radiative cooling for the last decade or so. And here it's about simultaneously controlling solar reflective properties as well as long-wave infrared properties. So historically, this has been primarily in terrestrial applications, and we've demonstrated the ability to make a broad range of materials that can passively cool themselves below the air temperature and could potentially serve as radiating surfaces for adjacent heat loads. And so in 2020, for instance, we demonstrated a range of low-cost coating and paint bead strategies to achieve this using materials like aluminum oxide and barium sulfate in a fluoropolymer binder that could be very suitable for both LEO as well as terrestrial applications. And so these are what we call super white paints, and we think there's a lot of applications for them. There was a paper in Joule that showed in 2020 how you could combine these kinds of surfaces with a concentrating architecture to improve the performance of the concentrating PV cell itself. So we think there's a lot of exciting possibilities here. My email address is right here. We'd love to touch base with anyone who finds any of this interesting. Thank you.
Next up is Tandem PV, and I have your slides. Can you see them via the web meeting?
I can, thank you.
All right, go ahead.
Hi, everyone. Colin Bailey from Tandem PV. If you could advance the slide. Now I can't see the slides anymore.
There's a little bit of a lag, yes.
Okay, there we go. We're a startup company in San Jose, California, about 30 people or so. And what we do is make mechanically stacked perovskite silicon tandems. You can advance the slide. We've talked a little bit about this with other presenters. What we do in particular is make 4-terminal or mechanically stacked perovskite silicon tandems for terrestrial applications, where we have a separate, electrically separate thin film monolithic solar panel made of perovskite that we stack on top of silicon cells. Some of the advantages here, I think, relevant to this solicitation are that we can control separately these two circuits. In the perovskite itself, we can control the output voltage of the panel and current for different native voltage and power requirements. And of course, from a failure durability perspective, the two circuits operate independently so that when mission critical events happen, to one of the two, the other circuit remains operational. If you could advance to the next slide. Here's a recent panel that we made. Actually, this is a little bit old. We're over 27% now between thin film, semi-transparent perovskite module on top of a silicon cell. What we do as a standard form factor, and that includes this, is 100 square centimeters, so 10 centimeters on each side. If you could advance to the next slide. Where we're moving this summer is to 300 square centimeters. I think this is probably fully responsive to the draft BAA goals. We should get well over 5 watts out of such a form factor. This is also compatible with a variety of silicon wafer sizes that are currently in use in commercial production. And what we've concentrated on, not only from the efficiency side as before, I think we're executing towards our planned goals. We should be at 28% here in the next month or so. And we still think we'll be at 30% by the end of the year, is to demonstrate what we think are commercial relevant durability targets that are also relevant for this solicitation or future solicitation. If you could advance the slide. We've focused on a variety of standard accelerated tests, so thermal cycling tests, humidity freeze tests, damping tests. So you see all of these are, unlike some of the previous presentations, focused pretty much on terrestrial applications, which is where our product design is intended. And if you'll advance one more slide. What we have a lot now in the field are these tandem solar panels in 2 locations. We've got about a dozen panels out on the roof at UC San Diego at a project. And again, apologies, this data is a little old. Now we're about 5 months in without any loss in performance in the perovskite over the course of the test. And we also have panels out at NREL in Colorado. If you could advance to the next slide. What we focus on in our own in-house testing is temperature-based durability as a function of running panels under what we think are operational conditions. So full sun, at operating voltages under a variety of different temperatures. And we think we're in the range of durability to be, responsive to having target performance lifetimes in the 3 to 10 year range for this solicitation. And then one more slide. So what we do right now is we make these panels in-house, perovskite panels that are interfaced with silicon cells. We would be interested in being a panel provider to a group who would lead a solicitation and generate an entire solution. Thank you very much.
Thank you. Next up is Boise State.
Tato Tanakar, professor at Boise State University. I just want to highlight some of our prior work, which was focused on a lot larger applications, but we've done a number of different spectral splitting hybrid projects for ARPA twice. One looked at kind of a more conventional light filtering approach with dichroic mirrors. Others looked at using a nanoparticle-based solution that filtered light off to keep the temperature low, but then also tried to harvest that thermal energy for other applications. All of those were large-scale tests and demonstrations, well over a square meter of total aperture for sure. We've also worked on a PV topping retrofit project that was RP project, where we looked at multi-junction PV cells where we designed a low-cost concentrator optics that could be used to basically put flux on CPV cells. So the goal was to kind of look at that for terrestrial application. We've done other projects where we've hybridized PV with other applications like desalination, where we're looking at doing different doping techniques to basically leverage that waste heat that's produced on the PV cell for other applications. And then the bottom right's less applicable here, but we certainly do even high temperature system design as well. Our capabilities with respect to computational modeling is really in multi-scale and multi-physics, whether that's down at thermal transport, CFD, structural, all combined together, whether it's transient or steady state. We've looked at that at both large and small scales, as well as ray tracing for a variety of different CPV type applications and high concentration solar applications. And lately we've been doing a lot of multi-physics, high topology optimizations. And additionally, we have a lot of capabilities for fabrication and characterizations. We've done a lot of work on UV-Vis NIR spectroscopy for different spectral splitting applications, transient plane source for thermal conductivity, a large range of different coatings and additive manufacturing techniques. And then we have a custom-built high-flux solar simulator that we can do rapid UV aging and thermal cycling, where we can do about 600 kilowatts per square meter of flux. And then the kind of picture in the middle is a self-healing composite that was developed with some colleagues for basically a high solar thermal application, but we have some capabilities in self-healing as well that could be applied to projects here at a system scale. And last, we're looking to partner with other projects. Our expertise is by far thermal management, optical properties, multi-physics optimization, and overall systems engineering. And that is my email, so I will stop there.
Thank you. Next up, Ascent Systems Technologies.
So basically, we are a small Canadian R&D company based in British Columbia. The company was born by inspiration from space industry, where I spent more than 25 years and in defense. What we have done, we have developed an integrated system, autonomous multi-purpose energy system as a module, self-contained module, which serves as a technology platform for the multiple applications, and it utilizes several energy generation and energy storage components inside to be able to use them for a number of other applications. Oh, I guess I need to just enable the slide sharing. Right. So it fits, specifically designed to fit into a standard shipping container, can be delivered anywhere in the world, and automatically deployed in less than 30 minutes. It is modular designed. It has a retractable PV array built and battery energy storage, and lots of sensors controlled by the onboard computer with machine learning algorithm. The control system is designed in collaboration with the University of British Columbia. This is the system the prototype of this platform was demonstrated at the Canadian Department of National Defence contest in Suffield, Alberta last year. It would show you, I will speed it up, how it would automatically deploy the stored PV array inside of the module. It would close itself, and it would automatically position itself in the proper orientation with the tracking toward the sun during the day. So basically what we are looking for now, we are doing the several applications, such as contract with the D&D for monitoring surveillance Canadian D&D assets in the Arctic. But the most interesting thing we are looking at is power beaming. Several years ago, I met Dr. Paul Jaffe from then National Naval Research Lab and now in DARPA, who is advocating and working closely in power beaming systems. We would like to enter that space because we have ability to incorporate practically any other technologies which were presented here or any which will be developed or emerging in the future. So the power beaming would allow us not only using the solar energy, but also the energy which would be beamed from any other sources targeted and utilized for any critical applications, like, such as remote bases, naval base, army camps, disaster relief operations, and number of, including space ground segment of the space application. That's my lightning talk, and it's my contacts. Thank you.
Thank you. Next up is SWRI.
Yeah, my name is Pablo Bueno. I'm a lead engineer here at Southwest Research Institute, not to be confused with SRI, our esteemed colleagues. We do get that a lot, so we are not the same research place, so this is a different presentation. I represent a fairly large organization, so I'm going to give a broad overview of what it is that we do. I do not have a whole lot of specifics as other of the presenters do. Southwest Research Institute is a non-for-profit organization in San Antonio. We've been around for about 77 years. We have a campus that spans about 1,500 acres in the middle of San Antonio with about 2,700 employees. And we have a lot of space here to do a lot of very different things. We have more than 1,300 patents, and we very routinely present and receive R&D awards for various different things that we do around here. So what exactly is it that Southwest Research fits into the R&D process? So we do not do a whole lot of fundamental science, and we definitely do not sell any products. We sit squarely in what's called the valley of death. So we bridge, fundamental and basic research, basically all the way up to product development. But again, we do not manufacture anything. So programs like Solstice are very much squarely in our wheelhouse. We do applied research. That's basically what we do and what we sell. We have we are organized into very different R&D organizations. I don't know at this point exactly which ones are going to be part of Solstice. However, you are more than welcome to contact me to see exactly what it is that you're interested in. We do have applied physics and applied power divisions. We do have a division that caters pretty much exclusively to the defense and the intelligence community. We have intelligence systems, which are working on anything that's autonomous, so autonomous vehicles. I work in mechanical engineering, which is probably the most diverse of all of our organizations. Our powertrain engineering division, they work, they're going to be basically working on anything that's batteries. And then our space and sciences, they're probably going to be working on the space track for Solstice. Some of the fields that we're involved in, chemistry and materials. So these are the people that are they do, like I said, a lot of work on very different areas. So we do nanoencapsulation, for example. We do a lot of work for food and healthcare. We also do a lot of material development, and we do a lot of material testing, both quasi-static and also high-rate testing. In terms of defense and security, we do a lot of weapons testing and a lot of armor testing. We also do a lot of modeling in those areas. So one of the things, for example, that we're involved in is a lot of micrometeoroid testing for solar arrays. So that's, again, something that we can do both for testing and also modeling. We do expect to be working on that area for Solstice. We do... And again, we do both testing and modeling in those areas. In terms of Earth and space, our space division is probably the one that's most widely known. They sent the New Horizons mission to Pluto. Right now, we also are Scott Bolton is the PI for the Juno mission in Jupiter. So we have the Cygnus satellites. So this is something that's also very much close and dear to our core mission. And it's something, again, where we can help you either, from a product development standpoint or packaging. Electronics and automation, again, this is something that where we can help in terms of autonomous vehicle development and deployment. And finally, energy and environment, which is, of course, kind of the main part of Solstice. So we're involved in pretty much anything that has to do with energy productions, from oil and gas to nuclear to renewable energy. That's something that where we can help. We do have our own PV field, for example, to do research in photovoltaics. We do supercritical fluids. So we feel that we pretty much have expertise in all areas that are going to be required for Solstice. We are both prepared to either go as a prime or as a partner if somebody wants it. As I mentioned, right now, we haven't made the decision which way we want to go.
Thank you.
But yeah, thank you.
And next up is Colorado School of Mines.
My name is Omid Bik, and I am with Colorado School of Mines. In this presentation, I'm going to talk about a hybrid power systems and power electronic building blocks that we have developed in our labs. I'll briefly discuss the architecture of the power systems that we have for spacecraft. It improves power density, reliability, and resilience. And then I'll discuss the necessity of platforming power electronic systems and controls within these hybrid power systems. And at the end, I'll discuss some of the solutions that we have developed for these challenges. And this architecture is what we have developed in our lab, and it's applicable to different types of spacecraft systems. We are using a common DC bus that we connect our energy sources. The main source is solar, but we have also other sources such as battery energy storage, RTGs, or a nuclear electric power system. Depending on the size of the spacecraft and the power requirements, we can connect these sources to this DC bus as well as connect the loads to this. One key element in this power system is defining the voltage level within the spacecraft. If we look at the heritage voltage, what we have in the spacecraft, they are below 200 volts. And the reason for that is if you look at the Paschen curves, we want to stay below the below the lowest breakdown voltage. Like International Space Station is 160 volt generation and 120 volt distribution. And most of our spacecraft are below 200 volts. But we have found a spot within the spacecraft, within the Paschen curve, that allows us to go to 1,000 volt and beyond. In this architecture, we included a nuclear electric propulsion in case if the spacecraft is larger spacecraft with megawatt scale power demand. But for a smaller spacecraft, the energy source would be mostly solar systems, and in combination with battery energy storage, and in long-term missions that are away from the sun, perhaps RTGs could be used. But one common element in all of these sources is the interface of these these sources and loads to the bus using power electronic converters. And this is where we ask the question, depending on the type of the source, we need different power electronic solutions. Is there a way that we can use or develop building blocks like platformizing these power electronic systems? How that helps? We can use those power electronic building blocks as interchangeable boards. It optimizes the spares and reduces the number of component count. It reduces the maintenance and enhances the long duration of in-space operations. So we call this plug and play power electronic solutions. And this is the solution that we have developed. we have developed this power electronic building block that can be formed into a DC to DC converter, DC to AC converter, AC to DC converter, or AC to AC converter. So essentially, it's a building block for any type of conversion system. It's standalone intelligent converter. So we are developing from the ground up. We have power electronic switches that we develop in the lab. These are on interchangeable and detachable boards. We have developed overcurrent and overvoltage protection. Essentially, this block stands as a self-sustained intelligent block that we can put together to perform any conversion types. We have achieved 5% improved power density and 12% increased reliability. Thank you.
You still have 30 seconds.
Oh, basically, I'll finish with this. Compared to state of the art, we have improved 5% power density, 12% reliability, and we are able to go to voltages up to 10 kilovolts. That concludes my presentation. Thank you.
Thank you. And next up will be Penn State, and I will get your slides ready.
Yeah.
Go ahead.
Hello, everyone. This is Lin Xiaozhu. I'm assistant professor from the Pennsylvania State University. We have the capability on photonic design, radial thermal management, energy harvesting, and thermochromic materials. So here I would like to highlight our capabilities. First, we have capability to design, fabricate, and test the radial thermal management to cool solar cells. Reduced temperature for a solar cell can translate to enhanced power conversion efficiency and prolong its lifespan. So we do that by using a combination of electromagnetic simulation, nanofabrication, spectroscopic thermal characterizations, and field testing. Second, we have capability to develop dual harvest system that can utilize sunlight and other resources at the same time and on the same area to enhance energy harvesting per unit area. Third, we have capability to design photonic thermochromic materials to achieve dynamic control of optical and thermal properties. Fourth, we have photonic design capability to control spectral and angular feature of optical and thermal property of a material. Here, I would like to highlight a few studies and publications. First, we have demonstrated for the first time radial cooling of solar absorbers by using a visibly transparent but thermal black body. Here we do that by maintaining the amount of sunlight absorption while reducing its temperature by as much as 13 degrees Celsius. This temperature reduction can translate to enhanced power conversion efficiency and prolong its lifespan. Second, recently we have developed a scheme for the first time to co-harvest sunlight and cold universe for producing photovoltaic electricity and sub-ambient cooling at the same time and from the same area. So experimentally, we achieve a significant photovoltaic electricity generation rate, as well as more than 5 degrees Celsius temperature reduction on the peak sunlight using the same area and at the same time. Importantly, the achieved energy benefits for this dual harvest system exceed a bare solar cell by more than 30%. Third, we have expertise for achieving nanophotonic thermochromic materials. Numerically, we have designed a dynamic emitter that can switch its emissivity from a low state to a high state near emissivity of unity. This is achieved by using a material called vanadium oxide as a phase change material. Experimentally, we have observed significant change of its emissivity upon its phase transition temperature. Lastly, our research is backed by our expertise to control spectral and angular features of emission. For example, in the past, we had developed a photonic crystal to achieve near unity emissivity in all the infrared wavelengths, while the structure is visibly transparent. As another example, we have built a resonator structure that can achieve a spectral selective thermal emission. We look forward to teaming opportunities. Thank you.
Thank you. And we have one more lightning talk, which is coming from Australia. So they sent us a video since it's about 5 a.m. there.
Hello, everyone. My name is Xiaoming Wen from RMIT University in Australia. My presentation is about lattice battery solar cell. the major energy loss in single junction solar cell include two parts. One is for hot carrier, hot fallen from hot carrier, this part, and then unabsorbed infrared, this part. So generally, the single junction solar cell has the efficiency limited 33%, this shock decrease limit. So what is a lattice battery solar cell? Lattice battery solar cell work in a revolutionary mechanism. Is a very new concept. It can harvest full spectral solar energy from UV to infrared and overcome simultaneously energy losses. And so the theoretical efficiency can exceed 70% because this uses a very new concept. Then the significant advantage of other solar cells include one is a very high efficiency and at the same time have the high stability because thermal energy is converted to electricity other than heating the material. So I have to introduce a new concept. Lattice energy reservoir is a unique feature in parallel perovskite with soft lattice. It is a dynamic nanodomain with a long lifetime, that's in second or hour. Under night illumination, the photon energy can be stored into lattice energy reservoir and generate the hot, something like this. That means this hot lattice energy reservoir has a higher potential energy and in space is non-uniformly distributed. Then when the electron move into this area, this domain, then this energy will drive its up convert to up the conduction band. So in lattice battery solar cell, perovskite infrared composite will be used as absorb. So it can harvest full solar emission from UV part and to infrared part. Then all this hot carrier energy and as well as the near infrared energy will all transfer to electricity. So this is a working process for lattice battery solar cell. In brief, the high energy photon will generate hot carrier, but the hot photon energy will store in the lattice energy reservoir. At the same time, the near infrared part will absorb or generate a full carrier and transfer to perovskite and up convert. So finally, output is electricity. So the significant difference with other solar cell is UV part, infrared, visible part, and the near infrared part all together to convert to electricity. And then this hot photon part will drive the near infrared part with up conversion. So finally, this lattice battery solar cell can have the 70% efficiency and also have a very high stability because it can significantly mitigate the degradation and the decomposition. So this solar cell can keep the low cost fabrication at the same time to significantly increase efficiency and also significantly increase lifetime. Thank you very much for your attention.
That concludes the program. That concludes the program part of today's meeting. So you're free to use the room for a while, and if you want to talk with each other. But thank you for coming.
I have a question. Any post meeting questions or whatever we can send to the same?
So if you have any questions about the draft BAA or about the content of the Proposers Day, send it to the Proposers Day email alias that you sent the same questions to. The government doesn't commit to answering them, but it'll help them define things in the BAA, because if they get the same question, they'll know that it needs to be clarified. Once the BAA has been released, it will have a provision for submitting questions, as was described during the contracting officer's briefing. That'll be you'll still email your questions, but again, but there's not going to be any one-on-one questions. Questions you ask answers will be provided to everybody.